In this video, we're going to take a look at some simple but really useful properties of linear transformations, right? So hopefully we're getting more and more comfortable with the idea of these linear transformations and how they change one vector into the next. And now we just want to establish some useful properties, right? So let's actually start with a theorem, right? And it says, let T that goes from Rn to Rm, the familiar setup now, be a linear transformation. Right? And one of the first important consequences of this is this basically says if you have a linear transformation and if you try to find the image of the zero vector in Rn, so this is the zero vector in Rn, then it turns out you are going to get the zero vector in Rm. So like this, right? So this vector here is this is the zero vector in Rn, this is the zero vector in Rm, and if the transformation is linear, right, and we looked at the definition of a linear transformation previously, then this property has to be true. So basically what this says is that the image of the zero vector must be a zero vector, right, provided T is linear. Right, so provided T is linear. All right. Okay, so that one's pretty helpful. Another property is that if you have if we take the transform of negative u, right, that will always be the negative of the transform of u, and this is for all u in Rn, right? And this one, it should remind you of that property that's a part of the definition of a linear transformation, that if you have the transform of a scalar multiple of a vector, it's the same as the scalar multiple of the image of that vector, right? So again, a lot of these are fairly easy to prove. I'll prove a couple of them. Just so you can see what it looks like, but really it's just seeing what these properties are saying and then seeing how we can utilize them in other problems, right? So a third property is this: if you take the transform of u minus v, then what are you going to get? You're going to get the transform of u minus the transformation of v. And again, this is for all u and v in Rn, right? And then the fourth one is arguably the most important one. And it basically says, and I'll say it out in words first, if you take the transformation of a linear combination of vectors in Rn, you are going to get a linear combination of vectors in Rm, right? So this is what it looks like. Well, what would a linear a linear combination in Rn look like? It would be C1 times U1 plus C2 times U2 plus C, let's say K times UK, right? And here all the u's are vectors in Rn, and then all the scalars are obviously real numbers, right? So this is saying if you take the transformation of a linear combination of vectors in Rn, this is what you're left with. You end up with C1 times the image of U1 plus C2 times the image of U2 plus dot 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 CK times the image of UK, right? And the reason why this ends up being now a linear combination of vectors in Rm is because each of these images are in Rm. You know, yeah, it's kind of a lot to say, but this is a really powerful property of the linear transformation, in the sense that when you start with a linear combination of vectors in Rn, if you take their image or its image, you're going to get a linear combination of vectors in Rm, right? I think probably the most interesting one here, a lot of these really just end up using the definition. They end up using the definition. I'm just going to show you the proof of the first property, probably the simplest one. And this says the image of the zero vector in Rn is the zero vector in Rm. So I'll just do a proof of I. It's a nice little one-liner, right? And so let's start with something like this. So if we start with trying to transform the zero vector, well, the zero vector can be written as the scalar 0 times any vector v in my vector space Rn, right? So I can write this zero vector as the scalar times any vector in V. So I can write it like this. That's true. Because an easy way to form the zero vector is to take any vector in your vector space and then multiply it by the scalar 0. Like you would distribute the 0 to all the components, right? But by definition, we are allowed to factor out that scalar. That's one of the properties that we saw in a previous video. I can take the 0 out, so I have 0 out here, times the image of V. Well, no matter what the image of V is, if I multiply it by the 0 scalar, I'm going to get the 0 vector. So this will be the 0 vector, and this one will be an Rm. Right? So that's the simple little proof here, and this is true for any vector v in Rn. Right? So again, in words, the image of the 0 vector has to be a 0 vector. If that is not true, right, then your transformation cannot be linear, right? In fact, that is sometimes, not always, but it's sometimes an easy way to check to see if a transformation is linear. So in fact, to illustrate that, let's take a look at this example. In fact, we'll go through a couple examples now where we can utilize some of these properties. Right, so let's take a look at example 1. So here is my question. So here's my transformation, and this will go from R to R. So it's like one-dimensional Euclidean space, right? And what will my function do? So it will take a real number, I'm just going to call it x, and then it's going to add 2. So it's going to take the real number and add 2, right? So this looks like your, linear function where you talk about a slope and a y-intercept, right? So is that function a linear transformation? Right? Well, we could go through the same properties that we explored in a previous video, or we could make use of this, right? We could make use of this. Because think about what would happen now. If I did t of 0, I would end up with 0 plus 2, which is not equal to 0, right? So since if I take the transform of the number 0 under this function t, I would end up with 0 plus 2. But that doesn't give me back 0, right? So because it doesn't follow this property of linear transformations, then this function, which looks to us as being linear, it doesn't have the property of a linear transformation. Yeah, we might be able to graph it and say it looks like a line, but it doesn't follow the properties of a linear transformation, right? So a line is something geometric, but these properties of linear transformations are algebraic, right? So sometimes something that might look like a line and smells like a line and sounds like a line might not actually be a linear transformation, right? So since this is true, t is not a linear transformation, right? And that is sometimes hard for some people to kind of wrap their mind around. Why is it all of a sudden now we have one definition of something being linear being it as a geometric definition, and now we have something that's a algebraic definition? Well, that happens a lot. There are lots of concepts actually that have one way of defining it geometrically and then another way of defining it algebraically, right? And that's why we don't, so for instance, I'm not saying that this is not a linear function, right? It just is not a linear transformation, and that's the difference, all right? So let's take a look at another example. So let's say that, so let t that goes from R2 to R2, right, be linear, right, with the following properties, right? So let's say we know that this linear, or actually, let me say, be a linear transformation, right? Let's be clear about that. So we're talking about the algebraic properties of being a linear transformation with the following properties. So let's say that t of 1, 0, we know that that is to -5, right? So the transformation takes the vector 1, 0 and produces the image to -5, and it takes the vector 0, 1 and produces the image, let's say 3, 8, right? And notice what I've done. I've taken the standard basis vectors for R2 and I've simply said what the image of each of those standard basis vectors is under t, right? So I know what t does to our E1, and I know what t does to E2. So here are a couple questions. So part A and B. So A says, what is the image of this vector? Let's say 7, -5 under t. right? So how could we figure that out? We only know what the image of our standard basis vectors is under t, right? So again, we know that t of e1 is 2, -5. T of e2 is 3, 8. Well, the thing about the basis vector is that every vector in R2 can be written as a linear combination of 1, 0 and 0, 1. And we just had a property, we just looked at a property for linear transformations that says the transformation or the image of a linear combination in one vector space will be the linear combination of images in the other vector space. In other words, I can write the 7, -5 as a linear combination of 1, 0 and 0, 1. And then I can take the transformation of that linear combination to get this result. All right, so this is how it works. So we want to find the image of 7, -5. Well, again, based on what we did with the basis vectors and coordinates, I can find the coordinates of this vector relative to my ordered basis 1, 0, 0, 1. So I can write this as t of, so the 7, -5 can be written as 7 times the vector 1, 0, that's my e1, minus 5 times the vector 0, 1, which is my e2, right? And because t is linear, that was the key, I can use my properties and say I can break this up and take the transform of 7 times 1, 0 minus the transform of 5 times 0, 1. Right? So that's one of my properties, right? And then I can factor out the scalar. So I can pull the constant outside and say that this is 7 times the image of 1, 0, and then factor out that 5, say minus 5 times the image of the vector 0, 1. Right? So there it is. So we've expressed our vector in R2, right, uniquely as a linear combination of our standard basis vectors. Use the properties of our linear transformation. First, we split it into the difference of these two images, and then factor out the scalar. And now we're going to use this fact. That's going to go right here. And then this fact goes right here. So that's the whole idea. The image of a linear combination is going to be a linear combination of images. Okay? Sometimes it's just important to keep saying these things, so that again you get very accustomed to the terminology. So the image of 1, 0, well, that's the vector 2, -5. So I have 2, -5 there. And then minus 5 times the image of 0, 1, which is the 3, 8. Right? And then let's go ahead and do our vector operations to do our scalar multiplication. So we have 14, -35, and then minus 15 and 40. So here is the image now of the vector 7, -5. So 14 minus 15, that's -1. And then -35 minus 40 is -75. Right? So what this basically shows is if I happen to know the image of just my basis vectors, then I can find the image of any vector in that set of vectors, right? So I would have the ability to find the image of any vector in R2 just by knowing what the transformation does to each of the image, to each of the vectors in my standard basis, right? So that's part A. So then let's figure out now what is the standard matrix of this transformation. So what is the standard matrix of T? And remember, we stated that theorem at the end of the last video that said that every linear transformation from Rn to Rm has a standard matrix and can be represented in that matrix form. All right, so let's restate what the image is of our standard basis vector. So the image of 1, 0, that's 2, -5. The image of 0, 1, that's 3, 8, right? Well, to find the standard matrix, what we have to do is essentially kind of figure out what the transformation is, what's the image of every vector in R2, right? Well, I mean, we could do just like what we did in part A, right? I can write this vector uniquely as a linear combination of 1, 0 and 0, 1. So I can do that same process. And look at what it is. So it ends up being T of x times 1, 0. That would make sure I have the x in my first component there. And then plus y times 0, 1. Okay. And then let's see what happens. So then if I break this into two terms, so this will be the image of x times 1, 0 plus the image of y times 0, 1. Factor out the y and the y and the x, because again I know that t is linear and that's one of the properties. So this is x times the image of 1, 0. So it's basically the same process that we did in part B, but not with a specific vector now, but with every vector in R2. And then similarly factor out the y. So we have this. And then now use the fact that t of 1, 0 is 2, -5. So we have 2, -5. And then t of 0, 1 is 3, 8. So we have y and then 3, 8. So if I now add these together, look at what we get. We have the essentially now this is the general rule for the transformation. It takes the vector xy and produces this other vector 2x plus 3y and then minus 5x plus 8y, right? But this vector now can be written as the product of two matrices. So now looking at it in this form, here is the matrix form of the transformation. It's going to take all we have to do is look at the coefficients of my my entries. So 2, 3, -5, 8. And then if I put my xy there as my column, there you go. Right? So now we've shown that this linear transformation, right, can be performed by using this as its standard matrix and then my matrix multiplication. So the standard matrix of this transformation, and look at that, the columns of my matrix, right, end up being the exact same columns of the image of the standard basis vectors. So the first column is your 2, -5. The second column is your 3, 8, right? So the standard matrix, so let's write that down. So the standard matrix of T is that column that's made up by the images of our standard basis vectors. Okay, so there are a couple useful properties, some interesting things that warrant more thought. So, think about the properties, and I'll see you in the next video.